business cards. What's that from your questions? How the fuck are you?
My manager was so proud of himself. He's like, I got training, got like training. Wasn't that bad?
Hire someone else.
Hire an attorney. Okay.
I'm a big kind of part thing. Anybody wants someone in here to offer to? Wait, what did you say? Layout?
Oh, I didn't. It was like a bit. It wasn't German, but it was German.
Oh yeah, I selected the same, but she told me that
Why?
because like you have to back it up slightly. You have to back it up to like
I said because of
I said same, but she kind of. So is it an explanation of like where, how you have to have some other card? Yeah. Also, are you guys like paragraph like really? Yeah, right. It's like about your. It's like here's my value. Here's like first limit more than 0. Between sensuality. Because like it was get a lot. Yeah. So with that is that. Yeah, that's my thing.
I would really go and sit behind.
Yeah, I mean, I also just want to see I think now, I'm like, are you sure? I don't think you want to I was like, there's no average central user. Oh,
Yeah, I get that person. Yeah, it's really easy. We just want to be
but got people
just ask us questions. left on that. Or worse, hey Tom, you help, hey Art, you help, hey Ashley, you help. Hey Tom, no, this is you. Yeah, it's the same as anything else, it just takes
Okay, let's start today. So any doubts regarding the assignment? When was it due for what? It's due on Monday or it was due on Monday? It is still due, okay. So, yeah, do you have any questions? No questions. That's good. So midterm has been graded, it will be done by this week. So get your midterms back this week. Not physically back, but you at least get your points back, and then you can come and look at your papers during the office hours. Okay, so let's start with clustering. If you don't have any other questions to ask. So last time we finished hierarchical clustering. Do you have any questions on the contents that we discussed last time? I want to finish up these things fast and then discuss the more interesting things. Right, so this is one thing that we need to finish, clustering, and the other thing that we need to finish quickly is association rule mining. That is also actually very interesting, but we'll try to finish. It's old. It's interesting, but it's old. So we'll finish the old things fast, and then go into the new things. Did we do anything related to deep learning as so far? We did not. So we'll do that. We'll have to do that. We'll have a lot of time, I think. We'll have at least 3 to 4 classes to discuss good things. These are not bad, but better things. So let's see density-based clustering. By the way, where do you use clustering? In real-life applications. In cool applications, where do you use clustering? Can you give me an example? What? What? Grading is an interesting application. You do it yourself, then you understand. What?
Trading? Stocks?
Is it a stock? Give me an example.
Classify them as high vulnerability, low, something like that. High yielding, low yielding.
What happened? Oh, wait a moment, just one moment. Can you just drop this down? Or is it mechanical? No, mechanical or electronic, I don't know. So it's shining on you, right? You are having trouble.
I think I will move.
Oh, this is not a switch.
I think it's that one.
Which one?
Here.
It's a nice picture, Sedona I do, right? Oh no. That's not the one. Yeah, you are also having trouble, right? You're okay? push anything. There's so many buttons here. I don't know what to do with them. I don't think we can just pull one. Well, anyways, I'll try to see what we can do. Okay, yeah, give me an interesting example. So he said stock market. What is it? What example? Where in stock market clustering can be used?
Can we classify stocks based on their EV,
Based on what?
the risk factor with them?
Okay, so risk factor, yes, that's one good point. The stock market risk factor classification, what you can do is based on risks you can have different investment opportunities. So there are some low risks investment opportunities where you get like 0.02% interest, right? And then there are high risks. So yes, based on the risks. So what you do is you use past data to see how many people have lost their money. And so if there is a lot of percentage of people lose their money, then you say there is high risk. That you can do. Any other example?
Market segments.
Market what?
Segment,
What is that?
like high-end customers, low-end customers.
Oh yes, yes. High-end customers based on what they are buying, and you can then advertise different things to them. Yeah. So those are some interesting applications of clustering. It's not just grading. So let's discuss density-based clustering. So there is a different type of clustering, and we saw that K-means doesn't do very well when the density is varying, right? When the density is varying, it finds out weird clusters. And same for actually, hierarchical clustering is a little better with respect to density, but it's not there. So let's talk about density-based clustering. It's also called DB scan. So so the basic idea is very simple, that whichever points have a given have the density greater than a given threshold, just consider them to be one cluster. Right? So you have to have some threshold. So there has to be a lot of variables that you need to define in order to implement a density-based clustering algorithm. So let's define those variables one by one. So first of all, what you can do is, what you need to do is you need to define a neighborhood. Now, how many of you know what is a neighborhood? What is a neighborhood? Neighborhood of a point? It's a fancy term for distance. A fancy mathematical term for distance. So which means if you want to define a neighborhood, you have to have a distance. And you can define different types of distance. You can have Euclidean distance, you can have Manhattan distance, all those different types of distances you have. And based on the distance that you choose, the shape of the neighborhood changes. So now, what is a neighborhood? The neighborhood is any point that is within a particular distance. So there has to be a distance threshold. So that distance threshold here is EPS. That's what they call it. EPS. Now they have in the book. This is they means the book. Right? The book says EPS. Now the book makes a very strict assumption that this is Euclidean distance, because you can have circle only if you have Euclidean distance. Right? So, but you can have Manhattan distance. So if it is Manhattan distance, then you have a hypercube. Hypercube means cube in multiple dimensions. So, and if you have a Euclidean distance, you have a hypersphere. Right? The word you add hyper means a lot of dimensions. Right? So depends. So the circle, whether it will be a circle or it will be a square or it will be a triangle, depends upon the distance metric that you have chosen. And then you define a threshold. So EPS is a threshold. So if a particular point is within that threshold, then you call it a neighborhood. And then what you can do is you can define distance by the number of points you have in that neighborhood. You can define density, not distance. You can define density as the number of points that you have in a particular neighborhood. That can be a definition of density. Now, how do you cluster? That's simple. You have to have some initial points. You have to have initial clustering points. So then you say, okay, this point has its own cluster, and then you figure out what are the points that are there in the neighborhood of that point. You define an epsilon, so you choose an epsilon, you choose a distance, and you say that, okay, let's say X number of points are in the neighborhood. Then you increase the neighborhood, say to a certain threshold. And when the density decreases or changes, it might increase also. When the density increases or decreases by a certain amount, you stop and say that, okay, this is one cluster. So the algorithm is simple, it's not that difficult. So let's go into more details. Now the algorithm is simple, yes, but in order to implement you need to have some more definitions. So let's have some more definitions. So there are three things that we need to define: core points, border points, noise points. Let's see what are these. So the core points, so these points are in the interior of a density-based cluster. Okay. So a point is a core point if the number of points within a given neighborhood around that point exceeds the certain threshold min points. So now you have a threshold of the density. Okay. So number of points that are in the neighborhood. So you have min points. Min points is the threshold. So what does that threshold serve us? So what you will say is that you will take a point and you will choose a distance, and you will choose an epsilon which will give you the neighborhood. So you take a neighborhood of that point, and within that neighborhood you select the points that are inside the neighborhood. If those points increase the min points threshold, the number of points is more than min points, then you classify that initial point that you chose as core point. You call it a core point. Then you have border points. What is a border point? A border point is not a core point, but falls in the neighborhood of a core point. So whichever points are within the neighborhood of a core point, those are border points. But these border points are not core points themselves. They may not be core points. They may be core points, but they may not be core points themselves. Right? No, actually border points cannot be core points. So these border points are not core points, but they lie in the neighborhood of core points. Then what are noise points? A noise point is any point that is neither a core point nor a border point. So this figure shows an example. So if you look at B, so here I think min points is 7. So if you look at A, how many, and this is EPS, this is the neighborhood, this circle is the neighborhood. If you look at A, how many points are within the neighborhood? 1, 2, 3, 4, 5, 6. Oh yeah, including A, right? So including A, so that means around 7. So min points, that is 7. So min point, if you have a threshold 7, then A can be a core point. Right? Now let's look at B. So if we look at B, and this is the radius of EPS, so B is in the neighborhood of A, but B itself is not a core point. Why? Because if you look at the neighborhood, there is only 3 points here. So B is not a core point. Right? But B is a border point because it's in the neighborhood of A. Now if you look at C, C is not in the neighborhood of A. C is itself not a core point because there are only 3 points in the neighborhood. So C is not a core point, and C is also not in the neighborhood of A, so C is not a border point. So C becomes a noise point. Okay. So using these three definitions, let's see how, and the parameters, the EPS, mean points, and the distance. Let's see how we can do density-based scanning or clustering. Well, it shows another example. I think this example is a better example of noise points, core points, and border points. Right? So they are saying that, okay, have mean points equals 4. So if you look at this, then mean points is 1, 2, 3, 4, 5, 6, and plus this point, so 7 points. 7 points inside the neighborhood of this point, and mean points is 4, so this is a core point. If you look at B, and this point, then again it has 1, 2, 3, 4 points inside. So anything less than equal to 4, you don't call it core point. It has to be greater than. So anything less than equal to 4, you don't call it core point. So this becomes a border point. And this is a noise point because it's not in the neighborhood of A, but and also it has only 3 points inside the neighborhood. So this becomes a noise point. So now this is the algorithm. So what is this algorithm saying? It says that, okay, label all points as core, border, or noise points. So given a set of points, you can do that. That is easy to do. You can label it as a core, border, or noise points. Right? Then you eliminate noise points. Don't consider them. Then I put an edge between all core points that are within EPS of each other. So you have to put an edge between all core points. So just look at core points. Don't look at border points. Look at just core points and add edge between all core points that are EPS of each other, that are within that EPS neighborhood. Then make each group of connected core points into a separate cluster. Right? So after this step, you will have some connected core points. Right? You make them separate clusters. So if you make them separate clusters, then what you do? Assign each border point to one of the clusters of its associated core points. So let's see. Let's take an example. You will understand it. No, this is not a good example. Okay, let's go back to this one and take an example. Right? So here, what are the core points? So let's do it here. So this is a core point. Okay, is this a core point? This one? Is it? Why? So it has 1, 2, 3, 4, 5, 6. Yes, this is also a core point. So let's mark them with C. So that is a core point. Is this a core point? Why? Depends upon the radius. No? Can't say. So actually, if we don't draw the radius, it's difficult to say whether this is a core point itself or not. Okay, so then let's take an example on pen and paper. So this is dV dV scan example. So in the book there is Euclidean distance. Let's take Manhattan distance. So Manhattan distance is just the box, right? So let's just take Manhattan distance here. So let's say I have these points, just randomly assigning them. How will you cluster? So what we'll do is, let's say you have mean points. Mean point again is 4, right? I drew too many. And let's say the EPS is 1, right? Let's say EPS is 1, mean points is 4. So is this a core point? Let's redraw. I didn't realize that it will be overwhelming to have so many points. So let's just focus on 5 points. And let's have a mean points of 2. So let's say have a point here, then let's have a point here, have a point here, here, somewhere here. Yes, much more manageable. Let's say mean point is 2, or actually 3, let's say 3. And the EPS is 1, right? So is this a core point? So if the EPS is 1, then the neighborhood becomes this for this point, right? So is it a core point now? It's not. Is this one a core point? No. Is this a core point? So 1 becomes this 0.5. No. It's not a core point. I think nothing else is a core point. So let's make it EPS 2. If EPS is 2, then 1, so 2, 2. So let's take this 2, and then 2. This is the boundary. This is the boundary of this point. So is this a core point? Yes. So there's 1, 2, 3, 4, and mean point is 3. So this is a core point. Is this one a core point? Why? So it's something like this. Right. So this is a core point because 1, 2, 3, 4. So this is also a core point. Is this a core point? So 2, this, and 2 will be this. Yeah, this is also a core point. Is this a core point? Is this a core point? It's not a core point. But we don't know whether this is a border point or a noise point. We don't know. Because this is not in neighborhood of a core point. Now let's say, is this a core point? Is this a core point now? 1, 2, 3, 4, it's a core point. So this becomes a border point. Right? This becomes a border point. Now, all this, so this one is a core point. Yeah, I think this is also a core point. And this one, this is not a core point, but this is a border point. So you classify it like this, and you eliminate all noise points. There is no noise point, so you don't eliminate anything. Right? Now it says that okay, EPS is 2. You have to have an arrow between or an edge between two cluster or two core points which are within EPS 2. Right? So what edges do you have? You have edges between these two. Right? This is within EPS 2. Is this within EPS 2? Yes. You have. Is this and this between EPS 2? Yes. This one? Yes. This one as well as this one. Is this and this between EPS 2? Yeah. But this one and this one? Yes. And so is this. So it becomes a fully connected. Right? It's I think everything is within EPS 2. So you have edges between all possible clusters, the core points. Now the next thing that it says is that okay, take a border point. Right? What does it say? It says that okay, you assign each border point to one of the clusters of its associated core points. So this border point, has an associated core point of this because this core point's neighbor was this border point. Right? So then this border point gets this cluster. This border point gets the same cluster because it's a border point of this core point. Right? So what happens is if you use density-based clustering here with these parameters, you end up with a single cluster. Right? So do you understand how you do with density-based clustering? Got messy, but I hope I got the point across. So that's the DB scan algorithm. So what is the time and space complexity? I mean, it's pretty simple, you don't need to really do it. But it says that time complexity is order m multiplied by time to find points in EPS neighborhood, where m is the number of points. Now what is the time to find points in a neighborhood? How can you find points in a neighborhood? What? So why don't they have like exact time? What will be the worst case time to find points in a neighborhood?
Find equilibrium for all combinations, and those which are below cutoff is
Yes. So what is the complexity?
n square.
No.
n minus 1. n square.
No. For one point, it's just n. For a point, right? And you already have n points, so it's all in worst case. That's why in the worst case the complexity is m squared. Right? So the worst case complexity is m squared. So you can kind of minimize this complexity order m square. M square is not bad, but you can still try to minimize reduce the m square complexity. So they are saying that you can use certain data structures such as KD trees to minimize the time complexity of DB scan, but you don't need to understand those. And you may want to understand those, but you don't need them for exams. So it says from m square you can do m log n. Very good. Now the thing is, how do you determine EPS and mean points? I just chose it, 3 and 2. So based on what you decide, you will get different clusters. So if I had reduced mean points, I would get more clusters. Right? If I had reduced EPS, I might also get more clusters. So we need to determine mean points and EPS. So how do we do it? So it says that okay, the mean points and EPS are basically the function of the characteristic of the distance. So does the distance look like a circle or does it look like a square, and so on. So square encompasses more elements. Right? If I had a circle of the same radius, so if I go here, go back here, if I had a circle of the same radius in here, it might have eliminated this point. Right? So that might result in, what I'm saying is that if I have a circle like this, and it might have eliminated this point as a neighbor of C. So that means C might have not been a core point in that case. So it depends. So it remains the same. Mean point is 3, EPS is 2. But just by changing the distance metric, I can consider this as a border point instead of a core point. Right? The EPS and mean point remains the same. If I just had considered Euclidean distance. So this mean point and EPS choice depends upon the distance. So you have to kind of see what is the nature of the distance. How is the distance value? So it's saying that for points that belong to some cluster, the value of k is to be small if k is larger. So it's talking about the same thing. So they are now showing the different examples of sample data and what are the different types of clusters they obtain. So this is EPS 10, mean points 4. Then this was the original points was that, and they obtain this cluster. But if I increase, they didn't show the gradual increase. Okay, so the green ones are the core points, the blue ones are the border points, and the red ones are the noise points. Right? So if I just had the core points, it would have been fine. That those are the clusters, and ignore the border and noise. But what the DB scan does is that utilizing the core points, it refines the cluster. So after it refines the cluster, this is the cluster. So what are the strengths? The strength is you can have arbitrary shapes. You don't have to have globular structures. Because remember, K-means wanted globular structures. So does hierarchical clustering. Hierarchical clustering overcame the problem that you can have different sizes of cluster. K-means say that okay, even if globular clusters, if you have different sizes, then K-means gets confused. But hierarchical clustering doesn't get confused if you have different sizes of clusters. But then you still wanted globular. But DB scan can have weird shapes. It doesn't need to be globular. So that ends the first part of the cluster. So we'll go into the second part, evaluate different clustering mechanisms. We'll see how can we compare clustering mechanisms. Now, why is there a separate chapter? It's a separate chapter because the evaluation has to be done in an unsupervised environment. Right? So we don't know which ones are the clusters. We don't know. So if we don't know, how can we evaluate? And one method we saw that maybe SSE, sum of square error. But what are the other methods? So that's what we'll go to next. But before we go to that, do you have any questions? Yes.
You can't work with the anomaly points over here, right? In this
No, there is noise points are eliminated. Yeah.
So we won't be able to assign them to anything over here.
No. If your noise points are important, then DB scan is not good. Yes, so now you have to compare clustering algorithms. Which one is better? Which one do you use? The problem being, as we just discussed, that cluster is unsupervised. So we don't know what the clusters are. So how can we figure it out? So let's see. So these are some random points. What are the clusters? In these random points, different people will see it differently. So if you apply different algorithms, same, different answers. So K-means says this, 3 clusters. DB scan says this, totally different. And the hierarchical clustering is completely link means maximum distance. Right? If that gives another different result. So which one is correct? How do we say which one is good? Which one do we choose? There's no, we don't have any metric to compare. Often what people do is just combine all of them. First do k-means, then take their initialization as DB scan, or no, you first do DB scan, then take the clusters and initialize it as as the initial centroid of k-means, and then do the k-means clustering. That you can do. Yes.
You have said that we can't use SSE as an objective function, but what if you put a constraint that on the number of clusters? So that becomes a constrained optimization problem, and each point can't go to its own.
So how do you know what is the optimal constraint?
No, any constraint less than the number of total points, SSE can't be 0, right? So if you want like k clusters, you put the constraint as number of clusters to be k. So SSE cannot be 0 in that case.
But how do you know that that will give me the or what is your objective function in that case?
It will be an SSE, but
No, so that's the thing, right? So SSE, how do you know that reducing SSE is what you want?
in this case it can work, right? If we have the constraint that.
So okay, again coming back. So SSE, what does SSE do? What is the main task of SSE?
It minimizes the intra-cluster distance.
Intra-cluster distance, but does it maximize the inter-cluster distance?
In that aspect it fails.
It fails, right? So if it fails in that aspect, so if even if you optimize SSE, with respect to inter-cluster distance, it may not be optimal. So it doesn't even solve the purpose of maximizing inter-cluster distance by minimizing intra-cluster distance. Right? So that's why it's not advisable to use SSE as objective. Now the way that you are saying that, okay, have a constraint. So what constraint will you say? That the total number of clusters should be what?
If we don't have that constraint, then every point will go to its own cluster, as you said, and SSE will be 0. But if we have constraint that number of clusters should be less than the number of total points, so in that case,
Okay, so what will be the structure of that optimization problem? So this is an interesting question. So what he is asking, he's not asking, he's suggesting that let's have an optimization problem. Let's use SSE as objective function. We'll reduce it, but we'll add a constraint that the total number of clusters that you get has to be k, right? How do you formulate that in an optimization problem? What is the typical structure of an optimization problem? We know, right? We know the structure of an optimization problem. We have talked about that in SVM, support vector machines. We have formulated an objective function. So how do you write it? Now this is a good question actually. So how do you write it? You minimize we said C transpose X, and X is a vector. What is X? X is a vector of 1 to some n numbers, right? X is a vector of n numbers, and you want to find out X. Right? You want to figure out X, all these numbers. And then you have constraints such that some AX is less than B or less than equal to B of this form. So these are linear, it may not be integer and may be integer, but it's linear optimization problem, constraint linear optimization problem can be solved optimally. Right? You can solve it optimally. Now you are saying that, okay, I want to put a bound on the number of clusters. So which means you want to bound n, right? So you want to introduce a constraint that says, okay, cardinality of n cardinality of x is less than, is equal to k, right? Not even less than, is equal to k. Is this a linear constraint? Can you represent this as a linear constraint? You can if you have an identity matrix, an identity vector. Identity vector means if x1 is there, so identity, so it's like a bitmap. So you can, if you have a bitmap. Bitmap means bitmap I is equals 1 if xi belongs to x. Then you can say is that you multiply, so you have ones, all ones, and multiply it with I. So I can be like a column. So you multiply with I, that means this is summation of all i's. Right? So summation of all i's is equal to k. That's a linear constraint. This is a linear constraint. But this generation of bitmap, how will you generate the bitmap? This is a non-linear function. Right? So if you want to include that, constraining the cardinality of clusters, that increases the complexity of the problem, and there is no solution. For that type of non-linear constraint, there is no optimal solution. You have to, and there is no algorithm. So that's why using SSE is a problem. It's if you want to use SSE and have that as a constraint, then it is resulting in first of all non-linear optimization. That's fine. Quadratic optimization. So you can use SQB, right? Sequential quadratic program. But it is also including a constraint that cannot be formulated as objective, and it's not a linear constraint. That's why it's not advisable to use SSE. Okay, so then how can you evaluate? How can you compare the two different clustering algorithms? So there are many approaches. So determining the clustering tendency of a set of data. Now that is a very vague term. What is clustering tendency? So you have to distinguish whether non-random structure actually exists in the data or not. And so you have to figure it out. Basically, that's what they are saying. Look at the data and figure it out, that whether there is a tendency of clustering or not. So tendency of clustering means, let's say you have historically, you know, that people get new tires when they buy old cars. Right? So you buy new tires when you get old cars from manufacturers. People know that. So old cars and new tires, they should be in a single cluster. So now, if your clustering algorithm clusters old cars with new tires, then maybe it's good. So that is the first point. That is what it is saying. That you look at the data and and figure out some clustering tendency. And these two go together. Historically, I have seen that. And if a clustering algorithm classifies them in two separate clusters, then that means it's bad. So that's the first approach. Then you can also figure out the correct number of clusters. Let's say, for example, I use dbScan on your grades. I want 4 clusters, so I know how many clusters I need. The correct number of clusters, 4. But dbScan doesn't give me 4. It gives me 1. Everybody gets A. That don't want that. Right? So I say that no, I won't use dbScan. It's showing me uniform density. So instead I will use k-means and I will force it to have 4 clusters because I will give it 4 initial median points. Right? So somehow I know the correct number of clusters. So in this case, in the grading scenario, k-means is better than dbScan. Then the third approach is evaluating how well the results of a cluster analysis fit the data without reference to external information. Now this is again a very vague statement, but the exact manifestation is that okay, you did the clustering analysis, right? And you say let's take an example of weather patterns throughout the world. So using weather patterns, you can cluster different areas. So for example, Puerto Rico is similar to Miami. So you can say Miami and Puerto Rico has the same similar weather patterns. Right? So you know that information beforehand. But it's an information regarding the data. It's not an external information. It's an information regarding the data. So now you do the clustering analysis and you see that okay, how well does it really cluster Miami and Puerto Rico in the same cluster. It might falter in certain cases, but on an average it is fine. So it matches the nature of the data. The other thing is that you just do supervised. Supervised means you go somewhere and get some external information and you know that these two are in the same cluster. You know some information beforehand. So this is totally external information. So you have the class labels. You have the class labels and you use that to figure out whether this clustering is giving me the exact class labels or not. So that is supervised. And that is not in the essence of clustering. Because clustering is done in an unsupervised way. So and then the fifth is you can do comparing the results of 2 different sets of cluster analysis to determine which is better. So you can use the same algorithm on 2 different data sets and see which one. So let's say you are comparing dbScan and k-means. You apply k-means to 2 different data sets. You apply dbScan to 2 different data sets. And compare whether they are coming up with the same or totally different clusters. And that can be one way of determining which one is better. So these are very vague techniques actually. So the only reason for these being vague is because it's an unsupervised. We don't know the class labels. Then we can have some measure of cluster validity, which means whatever cluster we are giving or we are getting from the algorithm, are they valid clusters? What do we mean by valid clusters? It goes back to the initial notion that we want to minimize the inter-cluster distances and maximize the inter-cluster distances. And that is what we want to do. So, so we have some definitions such as cluster cohesion, cluster separation, and so on. So cluster cohesion represents the compactness or tightness of a cluster. So which determines how closely related the objects in the cluster are. and cluster separation means how distinct two objects on different clusters are. So these two. So cluster cohesion might be to measure cluster cohesion we can use SSE. SSE is a metric for cluster cohesion. Now, what is the metric for cluster separation? We will see in a little bit. So these are called internal indices. So whatever indices are unsupervised, which means you don't have any external information influencing your decision, those are internal indices. So SSE, for example, is an internal index. But if you have some external information and then you are using that to evaluate clusters, then that is called external indices. So SSE, you know, I'm not going over it again. Okay. Now these are cohesion and separation metrics. So cohesion metrics is a SSE. That is one example. Now what is separation metric? How do you measure separation? Because we know that SSE cannot measure separation. So cohesion cluster separation metrics are measure how distinct or well separated a cluster is from other clusters. So you have two definitions. So cohesion is just the sum of squares that we know. So x minus mi, sum over all clusters and overall, sum over all elements inside a cluster and sum over all clusters. And then the separation can be measured as the BS or SSB. What is this? Just the sum of squares of the medians. Right? So this is what it's saying. So overall mean of the data, there is an overall mean n. Right? And then there are cluster centroids. Right? So this is saying that, okay, how far is the cluster centroid, each individual cluster centroid, from the overall mean of the data. And overall mean is just one value. So m minus mi squared, and you multiply that with the size of the cluster. Now there is an interesting correlation of this with the entire data. Right? So BSS and WSS. So if you look at, if you just do some algebraic manipulation, I think it's there in the slide. Oh yeah, so if you do some algebraic manipulation, what you will find out is that the total sum of squares, which means it's the sole property of the data, it's not the property of the cluster, right? So total sum of squares, which means there is a cluster, there is a data mean, right? Data mean is C. So it's the mean over all data points, right? So you calculate the total sum of squares, which is x minus mean over all data points, and you do that for all data points, irrespective of clusters. So this is not related to the clusters, total error rate, or total sum of squares, TSS. But that comes out that it is equal to the SSE plus SSB. What is SSB? SSB is this one. BSS or SSB is the same thing. Separation by the between cluster sum of squares. So this is between cluster sum of squares. So if you calculate it like this, and this is SSE, you sum them up, and that has to be constant. It cannot vary, because that is the property of the data. So based on different clusters, the total sum of squares never varies. Only the SSE and BSS will vary. Right? So what do you want to do? Do you want to reduce SSE? Yes, I want to reduce SSE. But if I reduce SSE, then what happens? The BSS increases. The BSS increases. So what if, do you want BSS to be more, or do you want BSS to be less?
More.
Why do you want BSS to be more?
Isolated clusters.
Yes. So if you have isolated clusters, then BSS will be more. Right? So that is what they are taking some numerical examples and showing that, okay, one cluster, how much is WSS, BSS. So these are good for your exams. But and this is just mechanical. You can just look at the data and calculate. Then there is another measure, it's an internal measure. Internal measure means internal index, it means unsupervised. So that is the silhouette coefficient. So what is the silhouette coefficient? It is it's calculated in a weird way, but we will see an example and it will make it clear how you calculate it. So what you do, it combines both cohesion and separation basically. So let's see what you do to calculate it. So to compute the silhouette coefficient of a point I, follow 3 steps. Okay, calculate its average distance to all other objects in its cluster. So at this point you have the clusters and you are just evaluating them. So you take that point I, and then what you do is you calculate the distance to all other objects in its cluster and make an average. That is AI. So you got AI. Now you calculate its average distance to all objects in a cluster not containing that object. So then you have that cluster. So I is in a particular cluster. Forget about that particular cluster. You go to other clusters and you figure out the distances of this I with other points that are not in its own cluster. So find the minimum of these values with respect to all clusters. So minimum of the average distance. Okay. So find out the minimum. So which means that, okay, let's say there is a cluster I and then a cluster J. So you take I and calculate the distances of every point in cluster J and make an average. Then there is a cluster K. Take I, calculate distances of every point from I to every point in cluster K, take an average. So if you have 5 other clusters, you have 5 numbers, 5 average numbers. Then find the minimum of these values. Call it B1, BI. Right? Then for the I point, you calculate silhouette coefficient like that. SI is equal to BI minus AI divided by max of AI comma BI. Why? Why would I do that? What will that achieve? And how is it combining cohesion and separation? How is it combining cohesion and separation? And do you want SI to be very large or very low? What do you want? Large, positive or negative?
Positive.
Positive value. Why?
That means it's far from the other clusters.
So that means the top part, BI minus AI, that measures separation. Okay. So you want to increase the separation. And the bottom part, max of AI comma BI, that measures cohesion. Okay. So if it has a lower value, then that means it is more cohesive. So what you'll see is that SI has a maximum value of 1 and a minimum value of minus 1. Okay. Why? Because maximum value is 1 if AI is 0 and BI is infinite. And it will be 1. And minimum value of minus 1 if BI is 0 and AI is infinite. Okay. So you get minus 1. So a negative value is undesirable, it says, because you say that we will have large positive value. Negative value means what? That BI is less than AI. So what was BI? BI was between cluster distances and AI was within cluster. So that means it says that between cluster distance is less than intra-cluster. So that means you have a very big cluster and a very small cluster which is almost very close to the big cluster. Right? So that is undesirable. You should not have that. So now we can compute the average silhouette coefficient of a cluster by just averaging all the silhouette coefficient of points inside that cluster. Right? So now you can compute silhouette coefficient of each cluster and then compare. If the silhouette coefficient is more positive large value, then you know that those clusters are good. So so do we need to do an example of similar cluster, or do you understand? We'll see. If we will do a like a review session of final exam, right? So when if you need to discuss a example, we will discuss then. Because all these are important for a final exam. So then there is another measure of cluster validity, and you can use that. That measure uses correlation. So what is it saying? So if you are given the similarity matrix for a data set and the cluster levels from a cluster analysis of the data set, then we can evaluate the goodness by evaluating correlation between the actual similarity matrix and the ideal similarity matrix. So what is it saying actually? So what you have is that you have a data set and you know that some item is similar to the other item. Okay? So which means you have found out certain clusters. So you have 10 points, P1 through P10. You know that P1, P2 is similar, P2, P3 is similar. So P1, P2, P3 is one cluster, and P4, P5 is similar, P4, P5 is another cluster, P6, P7 is similar, those are clusters. So you have certain clusters. Now what is the ideal similarity matrix? The ideal similarity matrix is the identity matrix, 1. Everything is 1 among the clusters. But then there is an actual similarity matrix, which means what does the data say? So you say that okay, P1, P2 are in the same cluster. So that means they are exactly similar. That's what we want. If P1, P2 are in the same cluster, they are exactly similar. So the correlation between P1 and P2 should be 1. So that is the ideal similarity matrix. It's 1 in the diagonals and 0 everywhere else. But then actual data is not ideal. So even if you have plugged 2 points as similar in the same cluster, their correlation might be not 1. It might be less than 1. Right? So if it is less than 1, then so that is one case. The other case is P2 and P3 are in separate clusters, but their correlation is not typically 0. It is some maybe 0.3. It is less than 1, but it is 0.3, let's say. But still you have it in different clusters. So actually in practical world, similarity matrix will not be an identity matrix. Ideally you want it to be identity, but actually it won't be an identity matrix. So now a measure of cluster validity is to figure out the correlation between the actual matrix, actual similarity matrix and ideal similarity matrix. Right? So that is another way of figuring out validity. To understand what I am saying. So if we look at hierarchical clustering, we did an example, right? Hierarchical clustering example. Let's look at hierarchical clustering example. Now this is dissimilarity matrix. This is just not similarity, but you can convert it as a similarity matrix. Maybe do 1 minus the values, right? Or some transformation you do. So now if we think about dissimilarity matrix, let's think about dissimilarity matrix. Then what is the ideal matrix? Ideal dissimilarity matrix? What will be the ideal dissimilarity matrix here? Yeah, the diagonal is all 0 and all other points are large numbers. Right? So if you figure out the correlation, then what should be the value of correlation? Correlation between ideal dissimilarity matrix and actual dissimilarity matrix. What should it be? What should be the correlation between ideal similarity matrix and actual similarity matrix? In the ideal case, 1, right? What should be the correlation between ideal dissimilarity matrix and actual dissimilarity matrix? 1. Right? In the ideal case, we will have the same dissimilarity matrix. But what do we have when we do clustering? Oh, we don't have the update. We did it in class, right? We did it in class. We don't have the ideal. I forgot where it is. Okay. Now, ideally, what you are going to do is initially you are clubbing 3 and 6 together, right? So, if you have clubbing 3 and 6 together, so P3, P6 and P3, P6, they will have 0, right, in the diagonal term. But is the distance between P3 and P6 0? It's not. Right? So, there is still some dissimilarity between P3 and P6. So, that deviates from the ideal dissimilarity matrix. That results in deviation from the ideal dissimilarity matrix. So same for similarity also. Same for similarity. So that is what they are saying, that you can use this similarity matrix to figure out. Now we can do an example. Well, do we have an example? No. Okay, so the book has an example. We'll do that example in the book. In the next class, I'll bring the book and we'll do the example for ideal similarity matrix. Right. So right now, let's stop here, and when we meet next time, I'll show you the example.
Fine.